Alright, so from 6B, all we want to do is that one construction. 6C, we'll move on. 6C is tangents. And we'll start off with some easy constructions here and gradually get a bit more difficult. The first one is perhaps the most obvious tangent question, which is if you have a circle and you choose a point on the circle, can you find the tangent line at that point? So construct, let's phrase this slightly differently. Given a circle and a point P on the circle, construct the tangent at P. So we have a circle and we have a point P on the circle. I want to construct the unique tangent line through P. How do I do that? Turns out we've already done almost all of the work because we did the problem already where we wanted to construct the circle center, which is easy enough to do. Easiest way to write down the construction anyway is choose 3 points, draw that triangle, and then the circle center is the circumcenter of the triangle. So construct the center, O. Step 1. Construct the circle center O. What now? Now let's draw in the line OP. Here I'm only drawing the segment, but you can draw the infinite line if you want. 2, draw the line segment OP. And there's only one more step now. How do I get the tangent through P?
Erect a perpendicular to
Yeah,
P.
just erect a perpendicular. You can go both directions if you want. 3, erect a perpendicular from P. And you're done, because that perpendicular is the tangent. Alright, so pretty easy construction. The more difficult question then is, what if I have P off of the circle? If I have P off of the circle, then there's 2 tangent lines. How do I find them? Right, and this is of course the problem of these Greek mathematicians, these Greek geometers. We know the tangent lines exist. It's just can we actually? A modern day mathematician would just say they exist. So let's just draw them, right? Here they are. I know they exist. But to Greek mathematicians, it was always, can I construct them? So given a circle and a point P outside of the circle, construct the lines through P tangent to the circle. So there's P. Here's what we're gonna do. I'm just gonna lay out the whole thing all at once here. So let's say I've built these already. Here's my two tangents. 1, 2. I don't really care what we call these, how we call them X and Y. This points of tangency. And let's come in here and have our circle center as well. Oh. What's true about this angle?
Right.
Must be right, because it's a tangent, or sorry, yeah, because it's a tangent. So if that's a right angle, if that's a right angle, then what must be true about this line? Since this is the hypotenuse of a right triangle, if I drew the circumcenter, or sorry, the circumcircle of these three, of this triangle PXO, if I drew in its circumcircle, oops, wait, where's the, this must be a diameter, right? Because this is the hypotenuse of a right triangle. So what I really want to do is get the midpoint of that line segment. If I can construct this line, P to O, get its center, and then draw in this circle, that will give me these 2 points of intersection. And those 2 points of intersection can now allow us to construct the tangents. So let's make this precise. Let's write down all these steps, because I don't think I was entirely clear there, but here's a solution. So step 1, once again, let's build construct the circle center. Construct the circle center of O, and draw line OP. OP, there we go, straight line. Now we want the midpoint. We want the midpoint of OP. In my drawing, the midpoint lies somewhere right around here. But of course, depending on where P is, the midpoint might be either inside the circle, outside the circle, or sort of on the actual circle itself. Doesn't matter for the construction. I just want to point out that my drawing isn't necessarily generic. It's because I've chosen P to be fairly far away. Construct the midpoint, we'll call it M of OP. And 3, we'll draw the circle. Draw the circle centered at M through P or O. It gives the same circle regardless. Draw the circle centered at M through P or O, whatever. And yeah, this intersects the circle, the original circle, at 2 points, X and Y. For this circle meets the original circle, at 2 points, X And now, as we argued, these must be tangents, we'll write down the argument now, but now what you want to do is draw in px and py. So step 5, draw lines px and py. These are the desired tangents. And this is just because we won't be fancy with our proof here. We'll just write down the gist of it. This is because PXO, angle PXO, is equal to 90, which is the same as angle PYO. Precisely because PO is a diameter of the circle. Because PO is a diameter. Of the circumcircle. So a little bit fancier of a construction there, but still not difficult once you've seen it done. Any questions about that? Okay, we'll move on then. Those are the basic sort of tangent questions. Given a circle and a point, find the tangents. But there's a much more famous problem in geometry, and much more difficult. So when it comes to geometry, and the sort of Greek mathematicians of antiquity, we've mentioned some of the really famous ones. We've got Euclid, Archimedes, of course. I don't think we've talked about Archimedes in this class. There's another very famous Greek geometer, Apollonius. This is the problem of Apollonius, and probably the most famous problem or theorem in all of geometry. This dates back to 200 BC. And Apollonius' problem was, if I have 3 circles, if you give me 3 circles in any arrangement at all, could be overlapping, could be all tangent to each other, could be very spread out. If I have 3 circles drawn, can I find a 3rd circle that's tangent to all 3 of them? And this might put you in a situation where you take a circle that's sort of like that, tangent to all 3 of them. There's not usually a unique solution, by the way. You could have a circle like that, tangent to all 3 of them. So this is Apollonius' problem. Given 3 circles, can we construct another circle tangent to all of them? So, let's see. Construct a circle that is tangent to 3 given circles. With modern day geometry, algebra, the invent of Möbius transformations and stuff, this actually isn't very difficult. but just based on what we know, which is sort of the type of stuff Apollonius would have been working with, this is a really difficult problem. And it turns out he solved it. So Apollonius solved this. Problem is, though, he solved it in his work that's known to be called Tangencies, but it's a lost work. So we don't have any copies of this anymore. He solved this in his lost work, Tangencies. And it's a lost work, but we know he did it in Tangencies because, remember, Pappus, about 500 years later, 300 AD, he wrote about this. He wrote about how Apollonius had solved this, and he mentions a little bit about his proof. So, known because Pappus writes about it in 300 AD. So of course at the time, 300 AD, this was not a lost work. They still had access to this. I don't know actually when it became lost, but it did. So we didn't have a proof of it anymore. And this went unsolved for a long time. What's next? Just in terms of the timeline. So now we get to about 1600. And I need to remember this guy's name. I think it's Van Roomen. Not a famous mathematician by any standard. It is Van Roomen. Provides a solution. You'll never hear this guy's name ever again because he's not very famous at all. But then comes in another guy. I don't really know how to correctly pronounce his name. It's French. I'm just going to call him Viète. Viète provides a better solution. So sort of an interesting story here. These two guys were friends, but they were made friends over this particular problem. In fact, the story goes something like this. Van Roomen had some problem that I don't think was actually very difficult, but he posed it to all the mathematicians of Europe, except France. Don't know why, but he just left any French mathematicians completely off the books. So then one day the French king has this ambassador visiting, and he's showing off the city to the ambassador, and he's bragging about we have this and that, and we have all these learned people of all these professions, and the ambassador says, wait a second, you guys don't have any mathematicians, right? Because Van Roomen's catalog doesn't have any mathematicians in it. The king says, that's ridiculous, get me Viète. So Viète comes in, and he solves this problem that Van Roomen had posed in about 2 minutes. Doesn't take him very long at all. It's a polynomial degree 45 or something. Viète knows a lot about circles. He was able to solve it no problem. And then he posed a problem back to Van Roomen, which was the problem of Apollonius. He wanted to rediscover the lost proof. So Van Roomen looks at it. I'm amazed he was able to solve it because he really wasn't a particularly good mathematician. But he provides a solution. The problem is, it's not really up to the Euclidean standard. He uses hyperbolas. And of course we can't construct hyperbolas, we can construct circles. Which is kind of okay. Hyperbolas turn out to be very natural in this situation, but it uses hyperbolas. So can't be done with a compass and straight edge. So Viete looks at this and he says, you know, I guess I'll rediscover it myself. So he provides a better solution, an actual compass and straight edge solution. And over this process, they become friends. But anyway. Oh, and we sort of know that this is probably a plausible solution to actually rediscovering Apollonius's proof, because from what Pappus tells us, he doesn't write down the proof, but he gives some hints. And it looks like probably what Apollonius was doing. And I'll lay out his program for you. So Viete, to prove this, Viete proves several smaller cases first. So people usually refer to these, if you have 3 circles, the Apollonian problem, they usually just call that for short CCC, 3 circles. But what are the limiting cases of circles? You take a circle of infinite radius, grow the radius, you tend towards a line, right? So a circle of infinite radius is a line, a circle of 0 radius is just a point. So we're going to look at sort of all possible combinations of points, lines, and circles. So C will be a circle. P will be a point. And L is a line. And up here at the top of the pyramid, this is Apollonius' problem. That's CCC. And given 3 circles, I want to find a circle that's tangent to all 3 of them. But if I take one of those circles and I limit it down to a point or a line, you have 2 other cases. You can have, okay, 2 circles and a point, or 2 circles and a line. And Viete realizes if I can prove these 2, or if I can actually just, it should suffice just to prove 1, but if I can prove those, then I can use that to prove Apollonius. So he looks at these and he says, well, these are hard, but how about I take one of these circles and shrink it down to a point or a line? So now you have a CPP, CPL, or CLL. And the last set of possible combinations, take these circles and shrink them down to points and lines. You get PPP, PPL, PLL, and LLL. So we have all these different situations. Instead of looking at just 3 circles, we're going to look at all possible combinations of having 2 circles and a point and try to find a circle that's tangent to all of those. By the way, when I say tangent to a point, I of course just means passes through the point. And Viete sets out to prove all of these cases, starting from the bottom of this pyramid, because you can use these to prove the ones above them. And we've already proven 2 of these. 2 of these are very easy. If I have 3 points, how do I find the circle tangent to those 3 points, or through the 3 points? That's just the problem of finding the circumcircle of the given triangle, right? 3 points define the triangle. The unique circle through the 3 points is the circumcircle. So this is easy. If I want to construct the circle in this case, construct the circumcircle. And LLL, also very easy. What would I want to construct in this case? If I have 3 lines, find the circle tangent to all of them. Of course, non-parallel in this case. 3 lines defines a triangle, right? So if I want the circle tangent to all 3 sides of a triangle, I'm looking for the incircle. That's one thing I can construct. So this is also easy. Construct the incircle. And what Viete realizes is he realizes is sort of a simple fact, and that if I have, say, a solution, if I have 3 circles, and I have the unique, well, not a unique solution, but if I have a circle that's tangent to all 3 of them, if I adjust the radius of a circle, all I have to do to maintain my solution is adjust the radius of the other ones by the same amount. If I make this bigger, then this radius has to shrink smaller, but all the other external circles have to grow bigger as well, and they grow by the same amount. So he says, okay, in the CCC case, let's just take one of those circles and shrink it down to a point. So now you're in this situation. Now let's take another one of these, shrink it down to a point. Now you're in this situation. Take the 3rd circle, shrink it down to a point. Now you're in this situation. And we've already proven this, therefore we can sort of pass it through the chain. It's a clever idea. And what I want to do today, I don't have all time to do both of these today. I want to prove this one, PLL. So by the way, these 2 are very easy. Next up in difficulty, those 2. You'll see today they're not that hard, but they're harder than these 2. If you were to prove these directly, I believe the textbook does one of these. These are quite a bit more difficult, and then these get really hard, and then you have Apollonius' problem. So our problem today is PLL. So given 2 lines, and a point, construct a circle tangent to all 3. So I'm only going to prove one case here. Once we establish this proof, it'll be kind of clear how to do the other case. And my 2 cases will be either the lines are parallel or they're not. So we'll do the non-parallel case. We'll assume our 2 lines intersect at a point and call it R. And I probably want to extend this a little bit. I need more space. A, B. So our solution we prove only the case where the lines are non-parallel. Intersecting lines. So, step one, let's just let R be the point of intersection, so we can call the lines RA and RB. Let R be the point of intersection. And let A and B be 2 points on the lines, one from each. One from each. Here's P. Am I losing generality here? Is it, if I choose P to be between the lines? Is that something I can assume in my picture? What if P's out here? Does that matter? Well, remember, I'm only drawing this part of it, right? But these are infinite lines. So choosing P here between the two lines is the same as choosing P here, still between the two lines, right? So it doesn't actually matter. So P does land something like this. Let's draw in RP. So step 2, draw RP and draw, we know how to bisect angles. So let's bisect angle R. And draw the bisector of angle R. Next up, we're just going to choose any old point on the bisector. So we'll choose any old point. We'll call this point V. Choose any point on the bisector. And we're going to drop a perpendicular. We're going to drop a perpendicular to RA. Again, I want to remind you that this isn't just, I know that it exists, right? In lots of our proofs in the past, because we weren't doing actual constructions, we know this exists, so we just say, let this be the perpendicular bisector. Not the perpendicular bisector, just a perpendicular. We know it exists, so we say let it exist. But I'm not saying let it exist. I'm saying I know how to construct this. So actually draw it in. So, and construct a perpendicular from RA through U. Oh, how do I call it V? Choose any point on the bisector V. Sorry. And construct a perpendicular from RA through V. So don't really like the way I'm wording this, but somehow I now have to give rise to the fact that I want to call this point S. So let S be the foot of this perpendicular. Alright, what now? Well, V is on the perpendicular, or sorry, on the angle bisector. So V is equidistant from RA and RB. So if I draw the circle centered at V through S, that's going to be tangent to both of the original lines. Right? So now, draw the circle centered at V through S. This circle is tangent to RA and RB. And if it passed through P, we'd be done. And it should be clear to you that the reason it doesn't pass through P is just because I chose V to be wrong. But there is a choice of V that will do this, right? I just sort of had to slide the circle along, slide the point V along. So we need to move this. So our next step, what step are we on, by the way? 4 or 5?
4 was the last one we did.
4? All right. Next step is this line RP, this intersects the circle with 2 points. Let's just choose one of them. Doesn't actually matter which one you choose. Remind me to point out what happens if you choose the other one. But choose one of the points, call it Q. So step 5, let Q be one of the points of intersection of this circle with line RP. So here's where it gets kind of tricky. Here's the clever step, is I'm going to draw the line through P. We know how to construct this. I'm going to draw the line through P that's parallel to BQ. So we'll draw a line through P that's parallel to BQ, and I care about where this intersects the bisector. We'll call that point U. So 6, construct the line through P parallel to VQ, intersecting, or let's just say meeting the bisector of angle R at point U. And here we'll do the same thing. We'll do the same thing as we did with this circle, which is, or with this point V, which is we got the circle by dropping a perpendicular. Let's go to U. Let's drop a perpendicular. What comes after S? T. And we'll have it meet RA at point T. 7, drop a perpendicular from U meeting RA at point again, with the reminder that every single time we do these steps, it's not just it exists, it's that I can actually construct this, that we have a process for constructing it. And we'll do the same thing. We'll draw the circle centered at U. We'll draw the circle centered at U, passing through T. And my claim is that this circle goes through P. 8. Draw the circle centered at U through T. We claim P lies on the circle. And we're done. So there's the construction. We only did the non-parallel case. If they're parallel though, it shouldn't be too hard to see how you modify this. You can still get sort of this angle bisector just by taking the midpoint, the line that's sort of in between both of the parallel lines. It's not too hard to modify the argument. What would have happened if I chose this point for Q instead? If I chose Q prime there, well, we would have come into P, and remember what we did from P is we drew a parallel line to VQ. Here I would have drawn my parallel line going this way. I would have gotten U out here, and I would have ended up constructing the other solution. Right? This isn't the only circle that's parallel to RA and RB and passes through P. There's another one, but it lives way out there. We would have just constructed that circle instead. Proof. Why does P? Shouldn't have cluttered my drawing so much here. Let's see if I can salvage it. Yeah, this should be good enough. Here's P. Okay. Here's P. How do I show P lies on this circle? Well, I need to show that UP is a radius. So UP has the same length as UT. Right? We want to show UP is the same length as UT, so P lies on the circle. There's not a whole lot to do here. You'd want to go through and prove this, but it's very easy to prove. These two angles are right angles. Because these lines are parallel, those two angles are the same. By angle, triangle RSV is similar to triangle RTU. So easy to see that triangle RSV is similar to triangle RTU. And there's another pair of similar triangles in this picture. Well, because these are parallel, that angle and that angle are congruent, and so is that angle and that angle. And therefore, so is this third angle. So also very easy to see that triangle RVQ is similar to triangle RSV. UP. All right, so we've got this triangle here inside of this bigger triangle, and this triangle here inside of this bigger triangle. Do you believe me on both of those? Okay. What does that mean? Well, because because these two triangles are similar, they are in the same ratio in side length, so SV over TU is the same ratio as RV over RU. Right, so this side of this triangle compared to this side of the bigger triangle is the same ratio as this side of the small triangle over this side of the big triangle. But hold on, this compared to this is in the same ratio as this over this, because these triangles are similar. So this is in the same ratio as VQ over UP. So the first equality is from working with the first triangle. We have sort of two triangles and two equalities here. This is from working with the first similar triangles, this is from working with the second similar triangles. And all I have to do now is make a substitution. What's VQ equal? VQ is equal to SV. Since VQ equals SV, we have SV over TU is equal to SV over UP. And that gives us exactly what we wanted. What does this mean? Cross multiply, cancel the SVs. That means that UP is equal to UT. Exactly as we wanted. Since I called it a proof, we won't end with a tick. We'll end with a box. So much harder than the other kid, than the bottom of the pyramid, LLL, PPP, those are pretty easy. Now we've knocked out another one. This is obviously harder. But yeah, we're out of time, so we'll stop here. Thanks, guys.